we can start moving a little bit into, strictly speaking, next week's topics, namely relativistic dynamics. So from non-relativistic classical dynamics, we know what determines particles' trajectories. That's of course Newton's laws. Just everybody remembers what was Newton's first law.
Well, object was same rest or with the same constant acceleration and there's constant velocity and there's an external force that's acting on it. In which case it will accelerate in the direction of the net force.
Exactly. Very good. Does that still hold in relativity? An object, yes, right. If an object is at rest, then relativity won't make it moving. And if it's moving, it can transform into another frame in which it's moving, but if there's no force, it will still move at constant speed. Newton's second law relates both the force to acceleration and change of momentum. If we write this in terms of momentum, what does this force do in terms of momentum? How's force related to momentum? Essentially the definition of the force is a change of momentum over time, right? dp over dt. And as it turns out, this actually still holds in relativity as long as we write this properly as d over dt as the relativistic momentum gamma mv, as we have it here. We'll see that there's essentially an alternative way of writing force, so Ku as the P mu over the tau, well that's gamma dP mu over dt. But essentially all the force laws that we know of, in fact, obey Newton's law, Newton's second law, in this traditional form with derivative with respect to time. Just keep in mind that the momentum just has this Lorentz factor. So, I'll take one very simple example. If F is just a constant in the x direction, then of course, and we start out with p of time 0 equals 0. Then it's very simple to integrate this up. If that is constant, that of course just means that p, now we know everything only happens in x direction, so let's forget x here. So p of t is just f of t, right? But f times t. But p of t we can write from this. That's gamma of t, beta of t times mc, right? Okay. We can solve this either for gamma or for beta. But I think what we ultimately want is beta here. So this is mc beta over square root 1 minus beta squared. Understanding that beta is of course a function of time here. And so this was f times t. So that means we can calculate beta as a function of time. Just resolve this for beta is ft over mc over square root 1 plus squared, right? Okay, and then we have the velocity as a function of time. what happens to this if time goes to infinity? So if we let the force go forever and ever and ever, you expect, see the momentum will just keep increasing and increasing and increasing. What about the speed? What happens to beta if ft over mc squared is much larger than 1? Then the 1 we can forget. Then we have ft over mc divided by only this, ft over mc. So beta goes to 1, meaning the velocity approaches c, but it's always less than c. Because this is always larger than this, so this will always be less than 1. So we see, even if we keep increasing momentum, we keep putting energy into the particle, accelerate it, the momentum will increase, but the velocity will still never exceed the speed of light. And interested, we can of course calculate what x of t is. Well, you integrate from 0 to our time c times beta of t prime, and that is relatively easy. You have t over 1 plus something times t squared, so it gives us c squared over f sine 1 plus ft. Okay, so but the main point really is that you can increase the momentum here, exerting a force, but you never exceed the speed of light, as expected. All right, but now, so classically, if you apply a force, what is the energy that a particle gains when you apply force? Classically, we had energy gain per time due to some force F was force
velocity.
Times velocity. Very good, yes. So times u, right? So, of course, we know that is p over dt. Let's see if that still makes sense. If we do this relativistically. So, on the left-hand side here, if we have energy, so this would be d over dt gamma mc squared, right? Or d over